ಸಾಕು ಒಂದು ಪ್ಯಾರಾಗ್ರಾಫ್ ಬರಂಗೆ ಒಂದು
ಸಣ್ಣದು ಇಂಗ್ಲಿಷ್
ಯಾರು ಮಾಡಿದ್ರು ಯಾರ್ಯಾರು ಟಾಕ್ ಕೊಟ್ಟರು ಇಬ್ರು ಹೆಸರು ಬರಂಗೆ. ಆಮೇಲೆ ವಿ ಸೆಲೆಬ್ರೇಟೆಡ್ ನ್ಯಾಷನಲ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಡೇ ಅನ್ನೋದು SIT ಒಂದು SIT ಅಷ್ಟೇ. ಫಸ್ಟ್ SIT ಅಂಡರ್ ದಿ ಅಂಬ್ರಲಾ ಆಫ್ SCT ಅನ್ನಂಗೆ. ಆಯ್ತು 184 ಆಯ್ತು. ಪರವಾಗಿಲ್ವಾ? ನನ್ನ ಫೋನ್ ನಿಮ್ಮ ಹತ್ರ ಇಟ್ಕೊಂಡ್ಬಿಟ್ಟಿರಿ. ಬಾಲಾಜಿ ಫೋನ್ ಮಾಡಿದ ತಕ್ಷಣ ಹೇಳ್ಬಿಡಿ ನಂಗೆ ಬಾಲಾಜಿ ಸರ್ ನೀವು ಜಾಯ್ನ್ ಆಗಿದ ತಕ್ಷಣ ನಂಗೆ ಹೇಳಿ ಅಂತ. ಮಾತಾಡಕ್ಕಾಗಲ್ಲ. ಅದಕ್ಕೇನೆ ಪ್ರೆಸೆಂಟರ್ ಬರ್ತಾರೆ, ಅದಕ್ಕೆ ನಂಗೆ ಹೇಳ್ಬೇಕಲ್ವಾ. ಅವಾಗ ಹುಡುಕಿ ನಾನು ಎಸ್ ಬಾಲಾಜಿ ಅಂತ ಮೆಸೇಜ್ ಹಾಕಿದ್ದೀನಿ. ಮೆಸೇಜ್ ಇವಾಗ ಅಂತೆ ಅಂದ್ರು ವಾಟ್ಸಪ್ ಇಲ್ಲೆಲ್ಲ ಡಿಲೀಟ್ ಮಾಡೋದು. ಶೇರ್ ದಿಸ್ ಬೈ 5:45 ಅವಾಗ ಫೀಡ್ಬ್ಯಾಕ್ ಮಾಡಿದ್ರಲ್ವಾ ಚೇಂಜ್ ಮಾಡಿದ್ರಾ? ಚೇಂಜ್ ಮಾಡಿ ಅಷ್ಟು ಏನೇನು ಹಾಕ್ಬೇಕಂತ ಹೇಳಿ ತಾನೆ. ಸೆಷನ್ ಅನ್ನೋದಕ್ಕಿಂತ ಕಂಟೆಂಟ್ ಹೇಳ್ಬಿಡಿ ಅಷ್ಟೇ. Did the content help you to theoretical concepts with the real world? ಹಂಗೆ did the content help you to theoretical concepts with real world problems? ಇಲ್ಲದೆ ಹೋದ್ರೆ ಕಂಟೆಂಟ್ ತೆಗ್ದೇ ಬಿಡಿ, ಸೆಷನ್ ಹಾಕ್ಬಿಡಿ ಅಷ್ಟೇ. ಅಲ್ಲ, ಕಂಟೆಂಟ್ ತೆಗ್ದೇ ಬಿಡಿ. ಕನೆಕ್ಟ್. ಹಲೋ, ಗುಡ್ ಈವ್ನಿಂಗ್. ಯಾ ಟೆಲ್ ಮೀ. Okay. Have you registered? Have you not joined to WhatsApp group? Madam, you kindly put a WhatsApp for me. I will share the WhatsApp. Yeah, madam, తెలుసు, నాకే తెలుసు. ఏమంటే మేడం ఒక్క నిమిషం నువ్వు ఒక మెసేజ్ పుట్టండి వాట్సాప్ గా. నేను వాట్సాప్ లింక్ పుట్టాను. ఓకేనా? సేమ్ నంబర్ నా వాట్సాప్ లింక్. sir. Have you joined the session, sir? Name? Can you raise your hand, sir? Can you raise your hand? Yes, Balaji is involved. I made you as make a present. Have you unmute, sir? Unmuted. Unmute, sir. Okay. If you want another one, raise your hand, sir. Yes, sir. I've done. Exactly at 5 o'clock, I will start the session, sir. Okay, okay, sir. I will on the video, sir. You also, you can also on the video. ರವಿಕುಮಾರ್ ಇನ್ನೊಂದು ಮೆಸೇಜ್ ಹಾಕ್ಬಿಡಿ ಇವಾಗ ಕೈಂಡ್ಲಿ ಎವ್ರಿ ಒನ್ ಜಾಯಿನ್ ಅಂತ ಇಮಿಡಿಯೇಟ್ಲಿ ದ ಸೆಷನ್ ಅದನ್ನ ಹಾಕ್ಬಿಡಿ ಇವಾಗ ನೋ ಎವ್ರಿ ಒನ್ ಜಾಯಿನ್ ಅಂತ ಹಾಕಿ ಅದೇ ಇವಾಗ ಹಾಕಿದ್ರ ಹ್ಞೂ ಲಿಂಕ್ ಜೊತೆ ಹಾಕಿ ಅಷ್ಟೇ ಎವ್ರಿ ಒನ್ ಜಾಯಿನ್ ಅಂತ ಈ ಅಮ್ಮಂಗೆ ಇವಾಗ ಇದು ಕಳಿಸ್ಬೇಕಂತೆ ಸೊ ಮಗಪ್ಪ ಆಗ್ತೆ ಇರಿ ಇನ್ನೊಂದ್ಸತಿ ಹಾಕಿ ಇನ್ನೊಂದಷ್ಟು ಜನ ಇಲ್ಲ ಲಿಂಕ್ ನಾ ಈ ಅಮ್ಮಂಗೆ ಕೊಟ್ಟೆ ಬಿಡ್ತೀನಿ ಸಪ್ರೇಟ್ ಆಗಿ ಒಂದಷ್ಟು ಜನ ಏನ್ ಮಾಡಿದಾರೆ ಅಂದ್ರೆ ಅದೇ ಗೂಗಲ್ ಫಾರ್ಮ್ ಅಲ್ಲಿ ಹಾಕಿದ್ದಾರೆ ವಾಟ್ಸಪ್ ಗ್ರೂಪ್ ಸೇರಿಲ್ಲ ಎಲ್ಲಪ್ಪ ಈ ಮ್ಯಾಥು ಸೂನ್ ಅಂತ ಹಾಕಿ
Hello, sir. Whether I'm audible to you?
Yeah, it is audible, sir.
Vasan, sir?
Yeah, it is audible, sir.
Okay, fine, sir. Thank you. Yeah.
ರವಿಕುಮಾರ್ ಎಷ್ಟು ಜನ ಅಡ್ಮಿಟ್ ಆದ್ರಿ ಇವಾಗ ತೆಗೀರಿ. ಹೇಳ ಇವಾಗ ತೆಗೀರಿ, ಇವಾಗ ತೆಗೀರಿ. ರೂಪ ಅದ ನಿಮ್ಗೆ ಬಂದಿತ್ತಲ್ಲ ಅವರು ಹೇಳ್ತೀನಿ ಅವ್ರು ಅದು ಆಲ್ರೆಡಿ ಮಾಡಿದ್ರು. ಲೋಯರ್ ಅಂಡ್ ಅಲ್ಲ, ನಾನೇ ಇವಾಗ ಆಫ್ ಮಾಡಿದೆ. ಸ್ವಲ್ಪ ಸೈಡ್ಗೆ ಹೋಗ್ಲಾ ನೋಡಿ, ಮ್ಯಾಥ್ ಕಾಣ್ತಾ? ಈ ಮ್ಯಾಥ್ ಕಾಣಲ್ಲ. ಈ ಮ್ಯಾಥ್ 2025. ಸಾಕು ಬಿಡಿ, ಸಾಕು. ಯಾವ್ದಾರು ಒಂದು ಕೊಟ್ರೆ ಆಯ್ತು. ಪ್ರಿಂಟ್ ಕೊಡ್ಬೇಕಾ? ಇದೆಲ್ಲ ಇದು ಕೊಡೋದಕ್ಕಾಗಲ್ಲ, ಇದನ್ನ ಕೊಟ್ಬಿಡಿ. ಇದನ್ನ ಕೊಡೋದು ಅಷ್ಟೇ, ಬ್ರೋಚ್ ಇದನ್ನ ಇನ್ವಿಟೇಷನ್ ಅಷ್ಟೇ ಕೊಡೋದು, ಅವ್ರಿಗೆ. ಇದು ನಮ್ ಇದಕ್ಕೆ. ಇಲ್ಲಾಂದ್ರೆ ಒಂದು ಇದು ಕೊಟ್ಬಿಟ್ಟು ವಿ ಹ್ಯಾವ್ ಡನ್ ಅಂತ ಇನ್ವಿಟೇಷನ್ ಕೊಟ್ಬಿಟ್ಟು ಮಾಡಿದ್ವಿ ಅನ್ನೋದು ಒಂದು ಬರಂಗೆ, ವಿ ಸೆಲೆಬ್ರೇಟೆಡ್ ಅಂತ, ವಿ ಡಿಡ್ ಇಟ್ ಅಂತ. 5 ಗಂಟೆ ಆಗಿ ಹೋಯ್ತು ಸ್ಟಾರ್ಟ್ ಮಾಡೋಣ ಕಣ್ರಿ. Respected dignitaries on and off the dais, distinguished resource persons, esteemed faculty members, dear participants and students, a warm good evening to one and all. I, Dr. Vasant Kumar S, Associate Professor and Head, Department of Mathematics, Sheshatipuram Institute of Technology. It gives me immense pleasure and honor to welcome you all to the two-day national seminar on Expedition to the Matrix World, organized by the Department of Mathematics, Sheshadipuram Institute of Technology, Mysuru, under iMath 2025. In commemoration of National Mathematics Day, celebrating 138th birth anniversary of legendary mathematician Srinivasa Ramanujan. Linear algebra forms the backbone of modern science and engineering, and this seminar has been designed to explore its depth, applications, and relevance in today's data-driven and technology-oriented world. Through this seminar, we aim to ignite curiosity, enhance analytical thinking, and bridge theoretical concepts with real-world applications. It is my privilege to introduce our Day 1 resource person, Dr. Balaji S., Assistant Professor, Department of Mathematics, School of Advanced Science, Vellore Institute of Technology, Vellore. Dr. Balaji S. is an accomplished academician whose expertise and insights in linear algebra and its applications are highly valued. We are confident that today's session will be intellectually stimulating and impulsively beneficial to all participants. Sir, I welcome you, sir, for this seminar.
Thank you, sir. Yes.
I would also like to place on record my sincere appreciation to the management of Sheshadipuram Educational Trust, our principal, HODs, and all faculty members of their constant support and encouragement in organizing this national seminar. I welcome you all. My heartfelt thanks to the organizing committee, coordinators, faculty colleagues whose dedicated efforts have made this program possible. Once again, I warmly welcome all the participants who have joined us from various institutions across the country. I am sure that this seminar will be a rewarding and enriching academic experience for everyone. At last, we will have an interaction session. You people can raise your hand and clear your doubts. Thank you all, respected Dr. Balaji sir. Now I hand over the session to you, sir. Thank you.
Yeah, thank you, sir. Um, Good evening and good evening to all. Uh, I am happy
Welcome.
to, I am very much happy to be a part of this today's seminar, especially with the name of our the mathematical National Mathematical Day, Ramanujan's Day birthday. So I am very much happy about that. I would like to thank the organizer Vastakumar sir for inviting me for this talk, as well as that head of the department and the management of Sesadripuram Institute of Technology, Mysore. Uh, I would like to thank them. I also like to thank my own institute who is providing me such a environment to share the knowledge with other uh, students and faculties. And with this small thanking, I'll start my session. Okay. Sir, I'll share my screen. Please let me know whether it is visible first. Mhm. What about I'm not able to share it? Vasant sir,
Yeah, tell me, sir.
1 minute I will leave and I'll join. The sharing is not enabling 1 minute.
Okay,
Is it
okay,
okay?
okay, okay.
I quickly join. I quickly join.
Yeah, Dr. Chitra madam, you can tell me what you have been raised your hand. What's your is there any issues? You can raise down. ಏನಕ್ಕೆ ಹ್ಯಾಂಡ್ ರೈಸ್ ಮಾಡೋರಲ್ಲ, ಕೇಳಿದ್ರೆ ಏನು ಹೇಳ್ತಾನೆ ಇಲ್ಲ. ಇಷ್ಟೊಂದು ಜನ ಡಿಸೇಬಲ್ ಮಾಡೋದು ಮೈಕ್. ಇಲ್ಲ ಮೈಕ್ ಅವ್ರೇನೋ ತಿರ್ಗಾ ಆನ್ ಮಾಡ್ತೀನಿ ಅಂತ. Sir, what happened? Okay, sir. Dear participants, if you have any technical issues, then only raise your hands. Otherwise, kindly put your hands down. ಯಾರಪ್ಪ ವಿದ್ಯಾಶ್ರೀ ವಿ, ಇನ್ನೊಬ್ರು ಇದಾರಲ್ಲಪ್ಪ ವಿದ್ಯಾಶ್ರೀ. ಲಾಗಿನ್ ಆಗಿಲ್ಲ, ಚಂದ ಹೇಳಿದ್ರು, ಇವಾಗ ಸಕದಾಗಿ ಹೇಳಿದ್ರು ಕಣ್ರಿ ಇವರು. ಯಾರು ಡಾಕ್ಟರ್ ಡಿ ನಿತ್ಯ ಇವರೆಲ್ಲ ಏನಕ್ಕೆ ರೈಸ್ ಮಾಡೋರು ಹ್ಯಾಂಡ್, ನನ್ಗೆ ಅರ್ಥನೇ ಆಯ್ತಲ್ಲಪ್ಪ. ಹ್ಯಾಂಡ್ಸ್ ಡೌನ್. ಜಾಯಿನ್ ಆಗ್ತೀನಿ ಅಂದ್ರು. Shall I remove? You are supposed to raise your hand, sir. Then only I can. I am removing both the yeah, both I am removing. Both I have removed, sir. 400 members are joined. ಸಾಕು. ಈ ಸ್ಕ್ರೀನ್ ಶಾಟ್ ತಗೊಳ್ರಿ ಕುಮಾರ್, ಈ ಸ್ಕ್ರೀನ್ ಶಾಟ್ ತಗೊಳ್ರಿ. 400 ಇತ್ತು, ಅದು ನಾನು ಡಿಲೀಟ್ ಮಾಡಿ 399 ಸರಿ. ಅದಕ್ಕೆ ನಾನು ಮುಂಚೆನೆ ಮಾಡಿಸ್ಕೊಂಡಿದ್ದೆ ಕೆಲಸನ, ಯಾಕೋ ಆಗ್ತಾನೆ ಇಲ್ಲ. ಅವ್ರೇನೋ ಆಗ್ತಾ ಇಲ್ಲ ಅಂತ ಇದ್ರು. ಇನ್ನೊಂದ್ಸತಿ ಮೆಸೇಜ್ ಹಾಕಿ ರವಿಕುಮಾರ್, ಎವ್ರಿವನ್ ಜಾಯಿನ್ ಅಂತ. those who are not joined, ಇವಾಗ ಇನ್ನೊಂಥರ, those who are not joined kindly join for the meeting ಅಂತ. the session has been started, kindly join ಅಂತ ಹಾಕಿ. ಸರಿ, ಟೈಮು ಮೊದಲೇ ನೋಡ್ಕೊಂಡಿದ್ವಿ, ಅದಕ್ಕೇನೆ 2 ಸತಿ ವೆರಿಫೈ ಮಾಡಿದ್ದೀನಿ. ನೆನ್ನೆನೂ ಮಾಡಿದ್ದೀನಿ, ಇವತ್ತು ಮಾಡಿದ್ದೀನಿ. ಬಂದಿದ್ದಾರೆ, ಆದರೆ ಪ್ರೆಸೆಂಟೇ ಮಾಡ್ತಾ ಇಲ್ಲ. ನನಗೆ ಕೊಡಿ, ನಾನೇ ಶೇರ್ ಮಾಡ್ತೀನಿ ಅಂಬಿಡ್ಲ. ನನಗೆ ಕೊಡಿ ಸರ್, ನಾನೇ ಶೇರ್ ಮಾಡ್ಬಿಡ್ತೀನಿ ಅಂಬಿಡ್ಲ. ನೋಡಿ, ಡೌನ್ ಆಗೋಗುತ್ತೆ ಇದು. ಈ ಥರ ನಾವು ವೇಸ್ಟ್ ಮಾಡಕ್ಕೆ ಹೋಗ್ಬಾರ್ದು. ಎಚ್ ಏನಕ್ಕೆ ಹ್ಯಾಂಡ್ ರೈಸ್ ಮಾಡೋದು? ಅವಾಗ ಅವ್ರು ಬರೆಯೋಕ್ಕಾಗಲ್ವಲ್ರಿ, ಅವ್ರು ಬರೆಯೋಕ್ಕಾಗಲ್ವಲ್ಲ, ಅದೊಂದು ಪ್ರಾಬ್ಲಮ್ ಇದೆಯಲ್ಲ. ನೋಡಿ, ಸರ್ yes, I have made it. Now, can you share, sir? ಏನು ಹೇಳ್ತಾನೆ ಇಲ್ಲ, ಮಾತಾಡ್ತಾನೆ ಇಲ್ಲ. ಯಾರೋ 3 ಜನ ಓಕೆ ಅಂತ ಹಾಕೋರು ಅಷ್ಟೇ. ನಾವು ರೈಸ್ ಡೌನ್ ಮಾಡ್ಬೇಕು ಅಷ್ಟೇ. ಲಿಂಕ್ ಅಂತ ಕಳ್ಸಪ್ಪ. ಯಾರೋ ಇಬ್ರು ಲೆಫ್ಟೇ ಆಗೋದು ಗ್ರೂಪಿಂದ. ಈ ಥರ ಆದ್ರೆ ಹಿಂಗಾಗುತ್ತೆ, ಹಿಂಗೆ ಆಗ್ಬಾರ್ದು ಕಣ್ರಿ. is happening, sir? We have done that, right? Sir, can you share that PPT? I will share here itself from my side. Hmm. Sir, in that you have a share or presentation. See that, sir, option will be there. Presentation or that one. Screen share. Screen share. Huh. Huh. Okay, you share with me, sir. Declining ಆಯ್ತಾ ಇದೆ. Sir, in Meet, are you not able to visible that share option, sir? Huh. Hmm. Okay, sir. Wait. Ah, sir. For a time being, I will share, sir. It is in PDF format, sir. Apologies, sir. I have shared the PPT PDF. Start, sir. Start, sir.
Yeah.
Yeah, dear participants, sorry for the delay. Now the session is going to start.
Sir, whether I'm audible to you?
Yes, you are audible, sir.
Okay, sir. Okay. Um, uh, Dear audience, sorry for the interruption due to some technical issues. I couldn't able to share with my system. Okay, anyhow, I will start the session. Uh, First, I like to uh, say how I am going to handle these 2 hours. It is a quite lengthy and quite long. It is 2 hours is quite long. Anyhow, as a title suggests that an expedition to the matrix world. So the main theme of my talk is not to enter into deep calculation. Instead, I want to convey some insights or some interesting fact uh, in that matrix what you are going through. That's what I would like to discuss. It's like as the word expedition says that it's like a travel. Okay, you just like that you come and travel with me, and wherever I have seen some beauties or some important things, what I have seen in my perception also, I would like to share this with you. Uh, in the due course, what you can get is sometimes people may know that concept little bit earlier also, but nothing wrong in revisiting again. So the perception matters. That's what the whole idea. Okay, instead of going with the deep calculation kind of things, it's just like looking at the things with interest. We have to look at the things. That's what the main aim of this talk. So, sir, can you change the slides? Yeah. So I am very much interested in reading this linear algebra book, Introduction to Linear Algebra, and many books are there by Gilbert Strang. By the name Gilbert Strang, he is a MIT professor. Uh, he's a well-known mathematician who speaks math in nice way. I like his book, and with that, what I like to say that is he in his book he used this word modern engineering
Big
involves
message ಹಾಕಿ
matrices.
ಇವಾಗ ಎಲ್ರು ಜಾಯ್ನ್ ಆಗಿ ಅಂತ
That
ಮೆಸೇಜ್
everyone
ಹಾಕಿ
knows actually, but
ಎವ್ರಿವನ್
the
ಜಾಯ್ನ್
words
ಅಂತ
are good
ಮೆಸೇಜ್ ಹಾಕಿ
and the modern engineering involves matrices. So anyhow, as I told, we are going to travel, but I have to fix something, then only I can reach some point. So in that sense, I would like to discuss about that. My talk is about understanding. Sir, you can move, sir. Sir, you can keep on moving. No, no, not this. I'm getting little delay here. First slide. Yeah, spectral theorem in R2. That's what I would like to discuss. Yeah, and especially in, as I said, it is understanding. So I keep the matrix version, especially in the 2 by 2 matrix case. Let's try to get the picture out of that. Okay. And the main, what you mean by spectrum, don't think too much. It is eigenvalues only. Spectrum of a matrix eigenvalue. So that theorem, what I'm going to convey, we are going to see that it is through eigenvalue, eigenvectors, not only the definition, understanding the picture about eigen and eigenvector. That's what the theme, and some application using this matrix in a multiplication, etc. Okay, uh, come down, sir. Sir, 1 minute. Yeah, and that as a mathematical a matrix, a matrix if you take, it is a transformation. One can look at in transformation which preserves. It's a map which preserves the origin.
ಸೆಕ್ರೆಟರಿ
And if
ಸರ್
you
ಬಂದವ್ರ
give
ಜಾಯ್ನ್
any
ಆಗೋರು
line
ನೋಡ್ರಿ
passing through origin,
ಸೆಕ್ರೆಟರಿ ಸರ್ ಜಾಯ್ನ್ ಆಗೋರು ನೋಡಿ
and if you operate matrix on the
ಸೆಕ್ರೆಟರಿ
line,
ಸರ್ ಜಾಯ್ನ್
then you
ಆಗಿದ್ದಾರೆ ನೋಡಿ
multiply that vertex on the line, and take the map of that line, it will be again a line passing through origin. It may get rotated or stretched, but it is going to be a line passing through origin. Okay. Similarly, little move one dimensional large. If you draw any parallelogram with two vectors as one vertex is origin, then you can see that it preserves the parallelogram also. So matrix does this work. It when you're operating matrix with zero with matrix, the output is zero. The input is a line passing through origin. Then the output is also a line passing through origin. And next, the parallelogram, if you give input, so it gives the parallelogram. But it might have stretched or rotated, that we don't know. But at the end, it will be a parallelogram. Okay. And next slide, sir. So with this small introduction about this matrix, which has this property, let's move to the next slide. The outline of the talk is, so insights of order. I would like, so even though I'm going to talk about the spectral theorem, to start with, we'll look at the matrix property first algebraically, okay? And then we'll go to the geometrical idea about this matrix. From the geometrical idea, we will get what we'll understand what is eigenvalue, eigenvector. And for special matrix, how it works. And once you understand this picture, then you can, you are ready to apply that concept in your application. Okay. So the insights, I'll go, as I said, here and there, there'll be some beautiful things will be there. So I'll start with some, just like looking at that world here and there, matrix world. Okay. So the insights of order means I'm talking about the commutative, not only matrix. By this time, I would like to tell you that you can view that one by a number as a one by one matrix. I hope matrix, I'm not going to
ರವಿಕುಮಾರ್
introduce the
ಸ್ಕ್ರೀನ್
matrix.
ಶೇರ್ ಆಗಿದೆ ಅಲ್ವಾ?
Everyone knows matrix. So you can, if I write a number 5, that you can view like it is a one by one matrix. Like that, 2 by 2 matrix you can create, 2 by 3 create, you can 4 by 4 square matrix, etc. etc. So, so in that sense, commutative, I'm going to talk for one dimensional, that is one number multiplying two numbers. And using brackets means associative. Now I'm moving to the dimension more. If you take a original matrix of some size m by n, then I can talk about the associativity. You know the property. As I said, it's the insights of that. Okay. And operations, multiplication. So I would like to see, I would like to discuss that commutativity, associative, multiplicative. We used to study in mathematics as like a property, axioms, as like it satisfies the group axioms, ring or matrix as a ring, etc., vector space. Okay. So here I would, since it is application point of view, all these properties are very much important in application. It matters. It matters a lot. That's what you're going to see. And after doing that, we'll understand the linear transformation. That is, our matrix is a linear transformation. With the example, we'll try to understand geometrically what it does. And two
ರವಿಕುಮಾರ್
special transformation. With that, I would like to give the picture about that theorem called
ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್
spectral theorem, and follows with the conclusive statement, the spectral theorem statement. As a
450 ಇದೆ,
mathematics
426
professor, as a mathematics teacher, and as a student, mathematics students, you should know the statement also. And next,
ಇನ್ನೊಂದು
the
ಸತಿ
next
ಹಾಕಿ ಮೆಸೇಜ್.
one slide. And next, we'll have that using the spectral theorem. If the time permits, I'll go with these two. Extension is SVD, and application using the SVD. SVD means singular value decomposition, and application is principal component analysis, called as PCA. And once you understand this, this is a very much important topic for your future. Okay. What is the AI and ML? They are concentrating on this idea. SVD is main. Okay. So next slide, sir. So as I said, I would like to, before looking at this slide, if
ಹೇಳಿ
you
ಎರಡು
people
ನಿಮಿಷ
having pen and paper,
5
you just write 2 2 multiplication 4, 2 star 4, write
ಸಾಕು
it one
ನಾವು
side, and 4 star 2. That means you are multiplying the two numbers, but I am writing in different way. 2 times of 4, 4 star 2. But as a number, this 2 times 4 is equal to 4 times 2. That is commutative property, okay? But you look at there is a 1 by 1 matrix also, and
Hmm?
I am looking at that in matrix also, okay? So what is, as far
ODL
as
ನಲ್ಲಿ ನೋಡಿದ್ರ
concerned, it is
secret
nothing, uh,
ಗೊತ್ತು.
we are not going to appreciate these things too much in mathematical way. Yeah, what is there? If I
ಹಾ
multiply 2
ಇಲ್ಲ
into 4, it is going to be equal
ಸೆಕ್ರೆಟರಿ
to 4
ಜನರಲ್
times 2.
ಸೆಕ್ರೆಟರಿ
But really in computer,
ಸೆಕ್ರೆಟರಿ
the
ಅಂತ ಜನ
earlier,
ಇರ್ತಾರೆ.
not now, I'm not, I
ಇಲ್ಲಾಂದ್ರೆ
used to tell
ಶೇಷಾದ್ರಿಪುರಂಗೆ
many things about this some
ಎಜುಕೇಶನಲ್
earlier
ಟ್ರಸ್ಟ್.
case that will give the insight about the subject, okay? So earlier, how matrix will multiply two numbers, it will create a copy of the numbers and it will add actually. Addition, multiplication is actually addition. So the first way, what I said, 2 star 4. In computer term,
ರಾಜರು
how it will calculate, it will take
ಅವರು ಕಳ್ಸಿಲ್ಲ ಕಣ್ರಿ
2
ಪರಿಸ್ಥಿತಿ.
4 times. Okay,
ಹಾ
2 star 4. That
ಕಳಿಸ್ತೀನಿ
means it will take 2 copies of 4. That means create the binary digit for 4, one bit, and another bit also create and will add it actually. But what is the other way? 4 cross 2 is it will take 4 copies of 2. That means it will create 4 memories actually, that bit, okay? 2 for 2, 1, first 2, second 2, like that, 2 plus 2 plus 2 plus 2. So this has some insights in computational algorithm actually, that when computer is doing, the way it matters. The 2 star 4 is quite convenient, better than that 4 star 2. That is 2 copies of 4 will minimize the memory actually, okay? So this I didn't put in slide because I want to make you to think a little bit. So similarly, now extend to one more. I would like to talk about this ABC. ABC means matrix. When I'm moving from one by one dimensional to the higher dimensional, a matrix of size m by n, then clearly that it is not commutative.
ಹಾ
Matrix
ಹಾಕ್ಬಿಡಿ ಅಷ್ಟೇ.
multiplication is not commutative. Now, but
ಅದು ನೆಟ್ವರ್ಕ್
associative
ತುಂಬಾ
law is true.
ಚೆನ್ನಾಗಿರ್ಬೇಕು
What do you mean by associative
ಮೀಟಿಗೆ.
law? I can if I take three matrices A, B, C, then multiplying AB and then multiplying this with C is equivalent to multiplying A times of BC. The bracket you can change. Both will be same. But as far as theory, it's okay. But really it matters in computation. Okay. So look at this example. We have done it. So next slide. You can look at this slide. This is A, B, C. Okay. Now, as I said, it is a cost of multiplication involves there. It is a big task in while writing the algorithm or programming. You have to take about that computational speed and the cost of that, everything you have to reduce. Okay. And you see, if A is a m by n matrix and B is n by p matrix, n cross p, then the cost of computing, you can check it with easy matrix, okay? Then the cost of computing AB will be, that means number of multiplication what you are using. You know how to multiply two matrix. You will take the dot product of the first row with the first column of the second matrix. So you will do the multiplication there. So count that. That will be equal to m times n times p. You can verify it, okay? So now this m and p matters, okay? Suppose you take this example, A is 10 by 100 matrix, B is 100 by 5 matrix. So A into B
ಸಾಕು
is
ಏನಪ್ಪ.
size 10 by 5 matrix. And first if I multiply A, B and then C, you will get C only that 7500 multiplication will come. According to our calculation, M into N into B you have to apply. Okay, for the first cost this AB. Okay, so you will get 7500. Similarly, if you do in other way, the cost will be more. It is 10 times more than this. 75,000 multiplication will come. So which one you'll prefer? The first one, as per the computation simplicity, that is preferred. Okay. So why I'm telling this example? What you have done in mathematics like axioms, as like theory, it has some meaningful in application. It is not like just you are having that. Those who have done this course in computational algorithm course, you may know these ideas already. Okay. But anyhow, I would like to discuss because it is all about the theory means you have to read the theory also. That's what I'm trying to say. That is important also. Okay. Next is sir, move, sir. Next slide. Yeah. Next here, first I talked about commutative operation property. Next I talked about I said about this something called associative property importance. Now the matrix multiplications also has some insight because we used to practice something in matrix actually from the school. They will give arbitrary matrix to us and we know how to find the determinant, the inverse, etc., etc. But in modern trend, the matrix from application will not have such a arbitrary matrix. It has some nice pattern, structure, etc., etc. Okay, even in my differential equation and this control system matrix, everything it has some nice structures. So once you come to that this engineering or undergraduate or postgraduate level, then you have to change your point of view. The matrix means it need not be with some m by n boxes with m by n places. You have to fill it in all places numbers. No, it's not like that. Especially from the nature as well as that application, what you are doing, it has some nice structures. So one example I would like to say, and we know how we are multiplying. We made that multiplication with the dot product idea, extension of dot product, and in certain rule we are multiplying. But it has some information when the matrix comes from the application, the way how we are doing the multiplication has some information. So this is a nice example. I have taken this from Gilbert Strang while I was reading this. I like this example very much. Uh, so it's a Pascal matrix. Everyone knows the Pascal triangle. You may have seen this. The way how I have written, you can understand that. And by the way, these Pascal matrix are coming from that coefficients of binomial expansion. I hope you understand this, right? Uh, so now with this matrix, I am going to form the, with this Pascal matrix, I am going to form the lower triangular matrix. Sir, one slide previous, please. Previous slide. Yeah. This is, I'm creating that 4 by 4 matrix. How I have done? This 1, 1, 1, we have taken the first column. And next 0, 1, 2, 3. Next 0, 0, 1, 3, like this. This I am forming an lower triangular matrix L. Is that clear? This is where we are doing that. One can create a full matrix also, but I would like to convey something. The matrix, what you are doing, it has some information. Okay, sir. Like that, you can, from the Pascal matrix, Pascal triangle, you can construct this matrix. Now, the similar thing, I have taken one more row, and you can see that it is a Pascal matrix with these Pascal triangle entries, and it is 5 by 5 now. And you know how to write this Pascal matrix, I hope. First is 1, next is 1, 1 you have to take, and next you have to take 1 plus 1 you have to keep always, and next entry you have to add these previous row numbers, 1 plus 1, 2, and next one is 1. Okay, like this here, keep on moving. So now what is the beauty in this? So next slide. Yeah, now I have taken this 5 by 5 Pascal matrix and I have multiplied. Okay, I hope you can verify it. It's going to be like this. You can multiply and check it. Now, this output matrix, 5 by 5 matrix, some information. What is that information? It's talking about something like a higher dimensional thing. Okay. And if you consider the first row, I am taking for, I am going to draw one things. Okay. See, this first column, the first column if you take, that is for 0 dimension. Okay. The second column you take it, name it as one dimensional object. And third column you take it as a 2-dimensional object, etc., etc. 3-dimensional object, 4-dimensional object. What do you mean by that? I will tell you. And you see that next slide, sir. Yeah. Now this is something I kept it as 1-dimensional now. Sir, one by one you go. One previous. One slide previous. Yeah. This is now dot is a 0 dimension. Okay. In a line. Dot is a zero-dimensional linear line. Okay. And what I'm doing now, take a copy of this dot and join by a line. What you'll get is a one-dimensional line in two-dimensional plane. Okay. The object now, here I am counting. This is my object now. Here I am counting how many one-dimensional object is there, how many zero-dimensional object is there. So two dots corresponds to zero-dimensional. This line is a one-dimensional. Is it clear? And what I'm going to proceed now, I'm going to keep on doing this. Take the copy of this object line and connect by this red line. Okay. Then you'll get a square, which is a two-dimensional object in three-dimensional. It is square. Okay. It is a two-dimensional. You will get this. And now you see, I am counting how many dots are there, how many lines are there, and how many squares are there. So in terms of dimension, how many zero-dimensional are there, how many one-dimensional objects are there, how many two-dimensional objects are there. Okay, now it is clear, right? What do we have? Four. What do we have? Four dots, four lines, and one square. Sir, can you go back to that matrix, the last matrix, 5 by 5 matrix? Back. Yeah, you see that. See, this is the corresponding to that first row is the first dot. Only one dot will be there. This one, the first row. The second row corresponds to the second diagram. There are two dots, one dimensional line. And if you see the third row, you can see that four dots, four lines, and one square, two-dimensional object. Okay. And next, now I have to copy of the square and I have to connect. And you can imagine without seeing the diagram, it is a cube. In cube, how many dots will be there? Corners? 8. And how many lines will be there? One dimensional. Two sides, how many square will be there? How many lines will be there? 12 lines will be there. 4 connecting 4. So 12 lines. And how many squares will be there? There is faces. How many faces will we have? 6 faces. Okay. And next to one cube will be there. And that's it. Okay. And the next column corresponds to something. Now you go to the diagram, sir. You can move. Yeah, this is a cube we have answered. Now, sir, don't move it. Now you look at this. And the next step is I want to take the copy of this cube and connect all the corners. That's what the game you are playing. Sir, can you move it? Yeah, you see, this is something in four-dimensional space. We are restricted to three-dimensional because as we are designed for three-dimensional only. So it doesn't mean that four-dimensional is not there. We can't confirm like that, but still our imagination is restricted because we are three-dimensional. And you see, this is a copy of the cube. Now I can ask the same question. How many zero-dimensional? There is how many points are there? How many lines are there, one-dimensional? How many squares are there? How many cubes are there? How many? This four-dimensional. This four-dimensional object is called tesseract. You can Google it. Lot of animations you will get. So this tesseract is a four-dimensional object. And graph theory, it's look like a graph theory stuff. So it's like a hypercube. The concept is the hypercube. Okay. So like this, you have to link that concepts. You have to switch over. You have to look at it in different ways. Is it clear? And now you count this number of points. Some of you count and keep it in mind. How many dots are there? How many? Sir, go back to the matrix. Yeah. Now you see that this will give that actually. Is it clear? 16 dots, 32 lines, 24 squares, 8 cube, and 1 tesseract, four-dimensional object. Now why? Now no need to stop. You can take the copy of the tesseract, the four-dimensional object, and do the same stuff. And if you ask this, what is the pattern there? That you can retrieve from this matrix. What I have to consider? Here I have considered up to 5-dimensional, 5, that is 5 by 5 case, 5 by 5 cases. So now increase one more here in this matrix from the Pascal. So that guy, the multiplication will give that stuff. How many zero objects in this, in with this rule, if you are constructing the diagram, it will answer that. Because geometry or diagram will not help you now, but algebra will help you. This algebra, what you are doing with multiplication will help you to go further. So this is one example will give you a lot of insights. Who knows, some matrix, because we always used to stop with only one, we look at the matrix alone. For example, if you take the graph theory, but people will work with this, but we'll stay with the matrix and study about the property of matrix. We won't go beyond. Sometimes for some case we'll go, for all we will not check. So it has some hidden, uh, what is that? The hidden truth about that theories or something will be hidden there after some taking a squared, a cube, a power 4, etc., etc. Okay, that is also you can look in that way. So in that sense, I like this example very much. Very often I used to discuss with my students. So I thought of giving, because as again I'm hitting the title only. Expedition, please keep it in mind. It is like a travel. Okay.
Huh?
Uh, let's keep. Uh,
ಮಾಡಕ್ಕಾಗಲ್ಲ.
sir, can
ಅಲ್ಲ
you move to the object?
ಎಷ್ಟು ಜನ ಅಂತ ಬರ್ತಾರಲ್ಲ.
The diagram. Yeah,
ಹ್ಮ್
this is the diagram. Okay. Now you can go about
ಅಲ್ಲಿ
this
ಮೇಲ್
also.
ಮೇಲ್
Now,
ಕಾಣುತ್ತಲ್ಲ ಕಂಟೆಂಟ್ ಎಷ್ಟು ಜನ ಅಂತ.
uh, so in this next slide is something you can't see the video actually.
ಹೌದಾ?
Okay, there will be some video actually coming, but it is due to some error. It can play with my system. But anyhow, I will tell that sir, previous, yeah. You go to that. You type this in Google after this. Sir, previous. The TED talk only. That. There is a book called Flatland. It is a book title written by that Abbott, Edwin Abbott. Okay, and the book is small book. It has a caption that a love for dimension. Okay, something a love. I think it's like that. It's a romance of dimension. Something like that. It will be there. Nice caption. And the people with the technology, they made the whole book as a video. TED Talk. In TED, TED Talk, it got this.
449
You will get some 3 or 5 minutes, at most 5 minutes
449.
video. It tells the essence of that whole book. Okay. It talks about the dimension. What I said now, it is pictured very clearly. I said we can't able to see 4 dimension. It may be there, high dimension may be there, but we are not restricted to, as our design is like this. That will be some argument with that in that book. You can, those who are interested, you can look at the book, and I suggest you to see this video. It is very nice. Okay, thanks to that TED, and this is one information. It will give some ideas to you. If you, in your way, if you look at the video, you will get some ideas. And at this point, these are all something algebraic way of looking at the matrix ideas, what we have already know about the matrix, but it has some insights. That's what my thought to keep these slides in this talk. At this end, do you have any doubt? You can ask. Any doubts, any questions are welcome. Any doubts? If you have any doubts, you can add any ideas. No, just it should not be monotonous, right? And keep on speaking, and that's what.
Participants, anyone having doubts?
Or any, you are not able to understand anything, because I was a bit fast actually.
Yeah, you can proceed, sir.
Okay, sir. Okay, then show that. So next few slides, I would like to make the platform for the spectral theorem. Okay. Before that, yeah, we'll try to understand. So for algebraic calculation, now we look at some geometrical insights of that matrix, what it does or what it will do when you are operating with some objects. Okay. You look at, I have given the name directly
ಯಾರು
for your
ಥಮ್ಸ್ ಅಪ್ ಮಾಡ್ತಾವ್ರೆ?
understanding. if you
ಯಾರೋ
all the
thumbs up
thing,
ಕೊಡ್ತವ್ರೆ.
now you see that in the diagram you are having a square. Okay, the square with vertices,
Huh?
it's like a parallelogram. It's like a square is a parallelogram, right? And you can see that it has that corners like 0 comma 0 vertex, and another corner as 1 comma 0, and another one is 1 comma 1, and another one is 0 comma 1. Okay, it is joined like that. Now we are don't read the words. Okay, first look at the matrix. The rule is, we know that this matrix preserves the line, any line. So if I take a red line which joining that 0 comma 0 and 1 comma 0, that means the whole line, it starts with this 0 comma 0 and 1 comma 0. Now take the n points, that is apply it here. That is this matrix times 0 comma 0 and this matrix times 0 1 comma 0. That means I am finding the image of 0 comma 0 and 1 comma 0 under this matrix multiplication. So matrix as like a map. It's mapping a vector in R2 to a plane, another plane, R2 plane. Okay, is that clear? So now you repeat this process for any two lines joining. Now there are four lines, red line, this line also there, 1 comma 0 to 1 comma 1, and 0 comma 1 0 to 0 comma 0 to 0 comma 1, and there is a line between 1 comma 1 and 0 comma 1 also. Okay, so you take in this way. Now you multiply. So whenever there is a line between two vector in this domain, you take the output of the two endpoint, then connect that images also. Like that, if you do, you can check it. Okay, can you try it? Any one of you? I need at least someone has to speak there. Sir, don't move the slide. Can you, with this instruction what I gave, can you tell me what will be the change in this square actually when multiplying by this whole matrix? Any idea?
I request the participants to those who have raised hand kindly hands down. Then only I can know that those who newly raised the hands, they will be having doubts. Rameshwara, Sophia, Shreyas, Siddhappa, Anusha, kindly raise down your hands.
Okay, sir, you can show the slide, we'll discuss. Yeah. Now you can see that the square after this, I hope some of you got this answer, those who worked out. So the square will become like this. Am I right? The whole square will become like this. It's look like initially those who are people used to answer like this, a reflection, but it's not a reflection. Reflection means the red line goes they has to stay on this. Somebody will say that this is a reflection about y-axis, but it is not true.
Ravi Kumar.
It is a rotation. Okay, as a name indicates, a rotation, and this matrix
One message
rotates that
chat
the
box
whole.
you can put a queries ಅಂತ ಹಾಕಿ.
The square by 90 degree. Okay.
If you have
So
any
this
doubts,
1 comma 0 90 rotation
put
will
a
go
question
to this 0
in
comma
a
1,
chat box ಅಂತ ಹಾಕಿ.
and this 1
WhatsApp
comma 1
group
will
ಅಲ್ಲಿ
go
ಹಾಕಿ.
to that minus 1 comma 1, and next this 0 comma will goes to minus 1 comma 0. According when you multiply and check it, you will get that. So you can draw the lines as I said with the rules. So it rotates. So what you got to observe? Matrix has some geometrical aspect. So when it operates on vector, because this object is from vector actually. The object what I have created is the use of vectors only in a plane, two-dimensional plane. So it moves the vector. It's in particular this example says that it can rotate the vector. It's rotating by 90 degree. Okay, not only the square, whatever vector if you take and multiply with this matrix, operate with this matrix, the output will be the vector will get rotated by 90 degree. So now the 90 degree can be generalized to any rotation also. You can write a general matrix. Okay. So next slide, sir. Next slide is reflection. As I said, the way how I have written it is a reflection about that x-axis. Okay, you can see that. You can show that, sir. Show the diagram. You can move. Yeah. Now you see that the red line on x-axis stays on x-axis because any vector on x-axis will be stay on x-axis only with respect to x-axis reflection. And you see 1 comma 1, the green, it comes to the direct reflection, the mirror image with the x as a mirror. This is goes to 1 comma minus 1. Okay, like this, 1 comma 0 comma 1 becomes 0 comma minus 1. So it is about the matrix does this work. It reflects about some axis. Okay, yeah. Next, sir. Yeah, next one is expansion and compression. So as the name indicates, see, look at the matrix expansion. I didn't touch that for both this matrix. The size is 2 by 2. Four numbers will be there. But you look at that, I kept only the diagonal. If your numbers are in the diagonal alone, then when you're operating on some vectors, it will scale only. Okay, it will scale. Scale means it will stretch or it will compress. Stretch the vector, compress. So the first one is going to be any vector. If you give here, it will take 2 times of that x, and if you multiply any vector x comma y with this matrix, then you'll get 2x 2y. So it's got twice of that. So the square become bigger. Sir, can you move the slide? One slide. Yeah. So now this 1 comma 1, this square unit square matrix, unit square becomes a square with size 2 actually because of this expansion. Similarly, 1 by 2, by this imagination, you can think it will go down actually, shrink. Okay. Sir, you can move the slide. Yes. So like this, so look at the matrix also. If there is no entry in that off diagonals or 0, only that non-zero numbers are there in diagonal, then it will do that expansion or compression alone. Okay. But if you invoke or if you enable some numbers in off diagonal, then it will create a problem. That's what the whole thing we are going to understand from this. Okay. The theorem is all about that only. Let's see. Next, sir. Next slide. Yeah. This is multi-scaling. So one can think, do we want to keep the scalar matrix? No. We can keep any non-zero numbers in that diagonal. So you can see here, this, you can move the slide, sir. It will go in 2 directions. This first column is for x variation. This second column multiply with y. So 2 times in horizontal, 3 times it will go in the height. Okay. So there is some multiple scaling or stretching. It happens, stretches. Okay. One more slide, sir. You can move. Shear. Now you see, the first time I'm introducing something in the half diagonal. Instead of that first row, second entry, I introduce 1. So now you see, previously you have some uniformity. It's not going away from that axis. Now this, due to
Exactly
this guy,
450.
1 introduced, it's
ಅರ್ಧ
not
ಜನ
only scaling,
50% ಬಂದವರು.
it's giving some shear. This action we call this shear. That means this x and y contributes for this action happened. There is no change in this x direction, but in y direction, the x plus y is coming. If you multiply this, operating this matrix with any xy, the output will be the first coordinate is x plus y and the second coordinate is y. Okay. So that's it. That's what that picture. So this is called shear. Those who are in mechanical stream, they may know this shear matrix. Am I right? Mathematically, what you have to understand, there is a contribution of both x and y here. This is the way you have to link mathematics with application. The right word you have to click, right word you have to use. Then only you can apply it in future. Okay. Okay. Up to this, what I kept it, I introduced first with the algebraic property. Next, I have shown with some simple matrix. It has some geometric nature. Now I'm going to use this technique. What you have seen in a matrix moves the vector, and we see there is some relation with that programming called computer graphics. Okay, and what I am going to discuss is not a current trend. It is some classical graphics idea. Okay, the matrix and computer, because the diagram itself will tell those who are in my age or my team, and they know this actually. The way that it is like in mobile and all, you have played this game, the monochrome computer, as like asteroid, and that all use the vector graphics actually. Now the reason advanced technique is there, it uses a lot of games with which uses the pixel directly. Okay, so here I'm going to talk about the basic application of matrix in some classical sense, but don't leave the classical word. The classical is much important for the futures. Okay, try to understand that old things always, that's a basic understanding, you can't leave that. Okay, so matrix and computer graphics, this diagram is like a space asteroid, something like that, you can play some spacecraft. All these things object you have seen here it's like a line or a polygon, etc., etc. Okay, so with this you can make use of the this matrix to play make the game. So next slide, quick. Yeah, you can move, sir. Move to the next slide. Yeah, here this what I said. Vector graphics refers to the previous one previous slide for one second. Yeah, vector graphics refers to the representing the images by mathematical description of geometric objects rather than by collections of pixels on the screen. So the later one is called raster graphics. Now we are going to talk about vector graphics. Okay, what we are going to do? Just we are going to take some object which has this square kind of things, what I have shown in the earlier example, and try to move here, and then we'll see according to the graphics what we need and how they are applying this matrix to do these jobs in computer. Okay, next slide, sir. Yeah, all these things we are going to do with matrix multiplication. Okay, we'll see that what do you mean by that. I'll directly go to that
Chat box ಅಲ್ಲಿ
any
ಏನಾರ ಮೆಸೇಜ್
polygon is
ಬಂದ್ರೆ ಹೇಳಿ.
created with the ideas this and all, you can see that. Next slide, sir. Next slide, you can go.
ಅದಕ್ಕೂ
Yeah, this is asteroid game. As I said,
ಹೌದಾ,
we
ನೀವು
are going to
ಮಾಡಕ್ಕಾಗಲ್ವಾ?
have, our ship will be here, we have control, and we have to move here without dashing with any
ಇವಾಗ
other
ಇಲ್ಲಿ ಬ್ಯಾಕ್ ಹೋಗಕ್ಕಾಗಲ್ಲ, ನಂದು
asteroids or
ಅದೊಂದೇ
so much
ಪ್ರಾಬ್ಲಮ್.
water coming, some space elements. Okay, like that the game will be there, and these are all, and the people, if you have played this, you may know this. You have to go either vertically or horizontally, like that. Movement will be like this. It will not be too quick as like what you are
ಯಾರು
playing
ಅಷ್ಟೇ
now.
ಇದೆ.
Okay,
ಹ್ಞೂ.
yeah. Next, sir.
ಯಾ.
Now we'll do a bit mathematics on this with the matrix idea. Yes. Now this is important. Now look at the ship. This is not new to you now. Already I have given the square. Now I have removed one line. I made it as a triangle. It's look like a ship. Consider it as a ship whose vertex are 0, 0 and 2, 0 and 1, 3 as placed like this. And this to implement on computer, we are doing the matrix. How to form? Just to take this vector and put it in column. Each vector in column wise. So this construct a matrix. Okay, but it is a 2 by 3 matrix. 2 rows, 3 columns. The whole diagram you can represent with this vector notation. Okay, with the understanding there is a line between that first column and second column and third column, and third column and the rotation 5 column. Sorry, first column. Okay. With this understanding, this matrix and this the construction, you might understand. Okay. Next. Yeah. Now to translate something. Okay. To translate the things, I can do this matrix operation. Okay. So this R is going to respond for R is going to get effect in the horizontal direction. There will be some translation or shift. It will happen in the X direction. And S is going to be in the units in the vertical direction. There will be a change. Okay. Now this matrix addition, because it is both are 2 by 3 matrix, so you can add entry wise. So the output will be R, 2 plus R, 1 plus R, S, S, and 3 plus S. Okay. Whatever input give, that much it will go in horizontal. If you give some R value, it will go up to R units in the X direction. It will move, and S direction above. This only this action will happen. Okay. But this we have achieved this translation by addition, but everything we want in terms of matrix multiplication. Okay. So how to achieve this? Next slide. So there comes that application point of view. They'll introduce some the next. Yeah. So now this is they call it as technically homogeneous coordinates. So in the new scheme, what will take? They'll take the triangle shape. That is the first two row represent that our shape, triangular shape, and they will introduce some dummy. This is I call it as dummy row. Okay. Everything about the shape we have to take it from these two rows only. But for the purpose of doing the matrix multiplication to get that required result, like a translation, then we are introducing this, and this will work. So the translation by R comma is now the product of these things. See now, you forget about this first matrix R and S. You assume that there is identity matrix. When I multiply identity matrix with this matrix, it will retain the same. But now introducing something like R, S in the last column. Okay. If you multiply this and if you do this, then it will translate that whole object R direction in the horizontal, and it will move vertical by S. Okay. The output you can see what we expected from our addition. R, 2 plus R, 1 plus R, S, S, 3 plus S. But this output we got it by multiplication. By introducing this 1 by 1, make it as a 3, then we got this. Okay. So in this way, one can do this homogeneous coordinate idea to get that scale translation by multiplication of two matrix. Next, sir. Next. Yeah. Now we'll do this actually. Suppose we want to fly our ship to 2 units in the direction. Okay. Uh, it is currently, that means facing up. So what do you have to introduce? There is no change in x. So r is 0 and take s equal to 2. The output will be this. Then the original, the vertex what you have to take is 0, comma 2, 2, comma 2, second column, 1, comma 5. So if you plot this with the same idea what I said, then this green original our ship will move to this blue position. Okay, the blue ship. Okay, so that is achieved by this translation. Next. Next. So translation I can do either I can move vertically or horizontally. I can use this translation. Now, as I introduced earlier rotation matrix, using the rotation matrix, you can do the rotation. So I especially shown that 90-degree rotation. Now instead, what you can do, in place of cos pi sin pi, if you introduce, okay, the first column is cos pi sin pi, second column is minus sin pi cos pi, if you introduce and take the 2 by 2 matrix,
Huh?
that will, when you're operating on any vector,
ವಿಡಿಯೋ
that will rotate a vector by pi
ಎಲ್ಲರೂ
angle,
ಒಂದು
the
ಸ್ವಲ್ಪ
theta angle,
ಮಾಡ್ಕೊಳ್ಳಿ,
whatever
ಹೆಂಗಿದ್ರು
theta
ಇಲ್ಲಿದೆ
or pi,
ಬೇಕಾರೆ
it's that
ಅದನ್ನ
much
ಎಡಿಟ್
angle it will rotate.
ಮಾಡ್ಕೊಡ್ಬೇಕಾಗತ್ತೆ.
Okay.
ಒಂದು
So,
ಸ್ವಲ್ಪ
sir,
ನಿಮಿಷ.
please next slide. So tanning, it happened by rotation. Okay. So again, you see here, it will happen by 90 rotation. What I said. See 90 rotation. You see here, and 3-dimensional they have done. In 3-dimensional they have taken like this. Okay. So in 3-dimensional you have to fix the column, and here it's happening between x y. Okay. So all the thing you have to understand this matrix multiplication will do the rotation. Already you have seen in the example also. So next, sir. Next slide. Yeah. Now you see the green one is something called original one. When I use this above matrix, the output is you got that you can plot it. You will see the rotation is something look, it's okay. As far as mathematical concern, it is okay. As like square, it got 90 rotation, you have seen in the exam itself. But as we are playing a game, it is a ship. There is no feeling at all. We can't move a ship like 90-degree like this actually. It's like a one step and next step is going like this. Okay, it's look little awkward. And if you may see what is there in this diagram, first diagram, it is near to that only, nothing, it's quite nice only like that. But if you look at that translated one, that I rotated by 90-degree, what will happen, it will look like this. So this is not good we feel about rotating an object. Okay, it's like taking some object and putting in this right hand side, turning and keeping like that. It is not like that. Now please everyone imagine we are in a bus or we are in a vehicle or we are in a ship, boat. Just we want to rotate ourselves to get a smooth turning. Okay, so that can be done with the combined. This is a rotation alone will not do. So what is the issue here? That rotation what we have seen so far, it will rotate about that origin of the plane. All this rotation will happen around fixing the origin. It will rotate the vectors about origin, some 90-degree or 120-degree, whatever it may be. But it is about origin. But when we want to create a game or something like to rotate an vehicle, we have to fix the center of that object. With that, you rotate. Then only that smooth thing will happen. Is that clear? So, how to do that? So, you have to combine both the idea. We have to merge the center of the object with the center of the axis, what you are having the plane, 0, comma 0 with center of this object. Then do the rotation, it will be smooth. That's what the next slide will show. Sir, can you show me? Can you move to the next slide, sir? Yeah, you see what I said is this, the center you can find it. It's a triangle, you can know how to find it. Calculation I'm giving to you, just the idea. Next, sir. So with this center, if you substitute in this matrix, and you see, we multiply on the left by the
Ravikumar,
original matrix is M of
already
that
ಯಾರೋ
ship.
ಫೀಡ್ಬ್ಯಾಕ್ ಕೇಳ್ತಾ
A.
ಇದ್ರು
A is something what you are going to do.
ಅಷ್ಟು ನೀವು ಕೊಟ್ಟಿದ್ರು
Any one of you?
ಫೀಡ್ಬ್ಯಾಕ್ ಕೇಳ್ತಾರೆ
The
already.
rotation it will do. And B is something that, what is that? Translation. It will translate that into
ಹಾ
the origin.
ಆಮೇಲೆ
It
ಹಾಕಿ
will fix the merge the origin. And again, you have to come back with A inverse. Okay.
ಹಾ
So the whole thing will do this. And you see, when you
ಇವಾಗಲೇ
multiply
ಕೊಡ್ಬೇಡಿ
this with our original matrix, you'll get the output like this.
ಬೇಡ
And you
ಬೇಡ
take the
ಇವಾಗಲೇ ಬೇಡ
first two row and each column, if you plot it as a vector, and you see how that diagram changes. So next slide, sir. Yeah, you see here, it will nicely rotate about that center. So the idea is all about the rotation, about which point that also matters. When you are saying something, the rotation matrix rotates about that origin. Now this is a rotation matrix, rotation about the center of the object, etc. Okay, like that. This the matrix has some nice application in this graphics. Okay, and this I'm skipping now. It's a cryptography now. It's a old trend. Now after computer, this can be cracked easily after an involvement of high technical things. So this you skip it, sir. Next. So up to this, what I have kept is something like classical way of looking at the matrix. Okay, the insights about the matrix algebraically, geometrical, and one classical example. Okay, but what is there in matrix till now? Okay, that's what we want to see. That comes with the idea about looking at that geometrical idea and how the matrix perform. That we'll see in the next few slides. Okay, next, sir. Next slide. Next, you can move. 2 or 3 slides after that only. Sir, previous slide. Previous. Okay, sir. You hold on this page. Sir, up to this, is the other audience have any doubts? or any queries? Because I'm going to the next thing, next idea.
Anyone having queries? Anyone having doubts? Raise your hands. Siddhappa,
Okay.
do you have any doubts? You can unmute and ask if you have any doubts. Sir, Siddhappa.
Okay, sir. Then I'll move. Okay, now what is displaying on the screen? Look at that and see, no need to read actually. If I ask you to read, how will you feel? Because usually we'll write the next slide. Can you move, sir? The same stuff like this. Can anyone can suggest what I'm trying to convey here? See, the reading, when I write in this fashion, it is quite easy for you to read it. Okay. I'm not saying you can't read in that fashion. You can read it, but still there is, if you see, there is some alignment with our eye parallel, and that this direction is okay. Both are in parallel actually. Line and this are in parallel alignment. And if you look at the previous slide, it is not like that. There is some angle made by with the line of our eye and that the way how I have written. Am I right? Is it clear? The previous slide. No, don't need to read this actually. This is some junk only. The previous slide. I want to know that how that. Now you see. But how can I make? But suppose this slide is very small one. You have many few lines only. But if you assume that you have some important thing in that fashion with that slanting version, then what we'll try to read very carefully, the mechanism we have in our head we can rotate, just tilting my head towards and make this eye parallel to that and we can read it, right? Then it's look like reading like this and in that direction. That's the whole thing, okay? So please take that crux. That's what we are going to do with the spectral theorem, okay? So this is, if it is like this slide, it is easy for us to do the things. Something is very clear. And the previous slide, if you compare, you need to do some work to do the things, to understand the things. So that idea, what I'm doing, uh, which makes it easier to understand. That's what we are trying to find with the matrix, okay? The idea, the one-line idea is this. Uh, so that we are going to crack with spectral theorem. Spectral theorem means, again I'm telling, spectrum means eigenvalues of a matrix. Okay. Next, sir. Next slide. Okay, to understand the spectral theorem, I'm not going to touch the statement I will give at last. Okay. Statement I will give you last. But we'll try to understand pictorially. Okay. So already you know, if I give some matrix to you, and the object I kept the same square matrix, the unit square, okay. And when you multiply this, you know now, some of you, those who have done this work, you know this. There is some 3 units,
Ravikumar,
there will be some scaling happen in
Rajaru
x
sir, join
direction,
ಆಗಿದ್ದಾರೆ ನೋಡಿ.
and there is no, nothing will be there in y direction, okay.
ಹೆಸರು ಸೇಮ್
So,
ಹೆಸರು
since
ಸೇಮ್
it's a
ಇರುತ್ತೆ.
diagonal matrix, I mentioned it is D, when you are operating on any object, it does this work. What it will do? It will stretch the given object only in x direction by 3 units. Okay, and there is no vertical change. So at this juncture, we can ask these questions: what is geometrically happen changes? The square input is a square. Inside this machine D, the output is some rectangle. Okay, this is about geometrical change. Assume that there is some mechanical mechanism or something like physical thing is happening. Okay, then you can answer this. There is some motion in x direction, and there is no motion in that object is not moving in y direction, only happening along the horizontal direction. Okay, the object is moving on horizontally, no vertical change. Similarly, when you are having the rubber sheet, something like it is stretching only along the x-axis,
Huh?
there is no change in the y-axis. Okay, so it is clear to understand this. It is clear to understand this. And you see, this comes from that
ಹೌದಾ?
important fact: there is no zeros, no non-zeros on the off diagonal. If you take this a principal diagonal 3 comma 1, if you look at
ಇಲ್ಲಿ
the
ಬನ್ನಿ
off
ಇಲ್ಲಿ.
diagonal entries, both are I kept 0. So the clear picture like this, it's coming from this structure called diagonal
ಬನ್ನಿ
matrix.
ಇಲ್ಲಿ
So
ರವಿಕುಮಾರ್.
diagonal matrix is easy to compare, easy to study. By seeing that, if you ask the determinant, you can tell immediately one of the
ವರ್ಷಿನಿ ಇಲ್ಲ.
property. Determinant is the product of
ನೋಡಿ ಇಲ್ಲಿ.
the,
ಇವಾಗ
what is
ನೋಡಿ
that?
ಇಲ್ಲಿ ಸರ್ಚ್ ಅಂತ ಹೊಡೆದ್ಬಿಟ್ರು.
Diagonals. Okay.
ಸರ್ಚ್ ಅಂತ
So
ಹೊಡೆದು
that is going to determine like this. Diagonal,
ಹಾಕಿ
even though if I
ರವಿಕುಮಾರ್
give a
ಅಂತ
big
ಕೊಟ್ರೆ ಬರುತ್ತೆ.
matrix, you can tell the determinant with this. So diagonal matrix is
ಅದೇ
easy to work on. But in general, an arbitrary matrix will not be diagonal. Even a matrix coming with application point of view will not have diagonal matrix.
ಶರಶ್ಚಂದ್ರ
Okay.
ಇದಾರಲ್ವಾ?
And then how we'll answer
ಸರ್ಚ್
this kind of question what I asked now? What is a physical change? What is a geometrical change, etc., etc. To convey this, next consider this S matrix. It is a 2 1 1 2. Okay, and
ಸಹನಾ
those who are very much
ಇಲ್ಲ,
understand are
ಶರಶ್
very known,
ಬರ್ತಾರ.
very well known about this matrix. It is a symmetric matrix.
ಅಲ್ಲ,
Okay,
ಅವ್ರು
you can
ಅಲ್ಲಿ
tell
ಹೆಸರು ಏನ್
something
ಕೊಟ್ಟಿದ್ದಾರೆ
about.
ಅದು
If I ask
ಹೇಳ್ಬೇಕು.
you to tell something about this matrix, you
ಎಸ್
can tell it
ಎಚ್
is a symmetric
ಎ
matrix.
ಆರ್
So now you see that
ಎ ಆರ್
I'm doing the
ಎಸ್.
same job. I am going to operate this matrix on this square, or else I'm going to input this square in this
ಅಲ್ಲ,
machine
ಅದೇನ್
S,
ನನ್ನ ಕ್ವಶನ್
and you
ನನ್ಗೆ
can see
ಹೇಳಿ
the
ಅನ್ನಿ,
output is
ನಾನು
going to be
ಕನ್ವೆ
like,
ಮಾಡ್ತೀನಿ ಅಷ್ಟೇ.
because now you can see there is off diagonal entries are non-zero. I kept 1 1.
ಚಾಟ್ ಬಾಕ್ಸ್ ಓಪನ್
Okay,
ಮಾಡಿ.
now you can see the diagrams. Sir, can you the next slide? Yeah, you see that geometrically somewhat
ಚಾಟ್ ಬಾಕ್ಸ್ ಯಾಕೆ
sir
ಓಪನ್ ಆಯ್ತಲ್ಲ?
previous. Yeah, so now you see that the last example, there is the diagram didn't come out of that axis. Now you see the red line came out of the axis, and it's settled in something in the first quadrant. Here also you see here, and the whole thing got stretched. Okay, and you see that if you ask the question, one question will be easy. The square becomes some parallelogram. Okay, geometrically you are achieved. And what happens to that mechanically or something if you ask physically? Some motion is, if you are moving, some objects are moving in this way, then it's moving in some range like this, okay, in this parallelogram way, because there contribution of x and y involved actually. So that you can see by take any x comma y vector and multiply this matrix, that will become the coordinate of the output will be 2x plus y, x plus 2y. Okay, so there is some contribution from x and y as well as. Okay, so that makes this, I am not saying you can't explain it, but you can't explain it is explain, or you can't view that very clearly. Now the word is important is clear. Okay, as like the previous case, you can't see the diagram like this, but one simple thing if I do, so next sir, next slide, one slide, next to move one slide. Yeah, now instead of taking the square, I have rotated the whole square by some angle rotation I have given. Rotation means this 1 comma 0 came here to the red line, okay, that arrow head, and similarly all the text moved, that you have to find actually. Okay, Why not? This I have rotated about 45 degree exactly. Okay. Now take these coordinates now, where the red arrowhead, green arrowhead, and this blue, and in with 0, comma 0, and apply. Give this matrix as this square. That is, I call it the rotated square as the input of this the same machine. Yes, sir. Can you move one slide? Yeah. Now you see that in this after rotation 45 degree direction, there is, if you see that red line, along the red line, there is stretch happens by some unit, and the blue line kept as like it is. So this action is happening. But what I have to do, groundwork, I have to do some rotation prior to that. Okay. So what is the crux? Now you compare with this, what I have shown in the first two slide in the read, as a read I have given now. Are able to compare it? Please, I need the answer for this. Then only I can move further. Are able to compare these two? Sir, previous slide you go, sir. Previous two slide. Previous. Yeah. This is something happening. Okay. This you keep it. This is like the read second slide. It's like our line, I line it parallel to that screen. Okay. Everything is something quite easy to understand, easy to read, something like that. The next diagram, the next page. Next, one more. Now it's like a tilted one. The read first I gave, no? That is the previous slide, the two diagram. Now this diagram tells about rotating the head and make it parallel to that first slide read. The next one. Yeah, one more. Now this look like the first tilted paragraph. No, please, previous, sorry. Yeah, this. Now this, what I have done, I have rotated the head. I am looking at it, looks fine. Okay, that means this all you can understand with that example. Now you see here, what is the crux? What is about the 45 degree I have told? How to find the direction? One may ask how you have rotated that 45 degree. That's all given by this eigenvalue eigenvector. That's it. Okay. That's all given by the eigenvalue eigenvector. The 45 degree, the direction I fixed, that will be the eigenvector, the direction of the eigenvector. Okay. So it's all on that eigenvector finding. Again, I'm not going to find the eigenvalue for this. If you find the eigenvalue, what you'll get? 1 and 3 will be the eigenvalue. Okay. And the eigenvector is going to be 1, comma 1 and minus 1, comma 1. Okay. Is it clear? Sir, go to the next slide, Move 2 slides after this. One more slide. Sir, no, sir, front. You go forward. Forward. Sir, move. After the statement, one more slide will come. After this, yeah. Oh, no. You went too far. Come back. Back, sir. Back. One more. You see there. You see here, sir. That one. Yes. This only. You see here, the whole matrix. The action happens. It is not easy to get the picture. Tell about something. Because there is both contribution from X and Y are there. X and Y are tightly packed, correlated. Okay, X and Y. Now I am switching over to a little bit statistical idea also. X and Y are two data. It's tightly packed. It is correlated. So now, but there is a technique to break this matrix into these three matrices via eigenvalue eigenvector. Again, I am saying that I'm not going to touch that definition of eigenvalue eigenvector. Instead, I gave that idea. What I will tell you. See that you see here, these 3 and 1 are going to be the eigenvalue, And these vectors, the first matrix, 1 by root 2, 1 by root 2, that is the first column. That is the first eigenvector corresponds to 3. And minus 1 by root 2, comma 1 by root 2, that is the eigenvector correspond to the second eigenvalue, 1. So once you have this, you take the leftmost matrix as some P. This is D. This is P inverse. But what is the beauty for the symmetric matrix? This, the decomposition, what you are doing here, no? This is going to be the diagonal matrix. This is going to be the orthogonal matrix. So we can choose an orthonormal vectors for the column, and you can break like this. All the thing, what is the mechanism? For a given symmetry matrix, find the eigenvalue and find the eigenvector. The way how we are going to find it automatically will end up with, you can find it orthogonal vectors for eigenvectors and put it as a matrix. This you form this a model matrix. So this, what you are having here, this 1 by root 2 minus 1 by root 2, 1 by root 2, 1 by root 2, the leftmost matrix, that will do the job of rotating. Okay. And this guy will do the scaling. And again, this guy will do the same. Okay. That's the whole idea. So what is the importance about the orthogonal matrix? That is a column with orthonormal vectors. Its inverse is same. Okay. Q transpose is identity. So that the inverse of orthonormal matrix is transpose. It's transpose. The inverse is nothing but just to transpose it. Suppose this is a matrix, this is orthonormal matrix, its inverse is the transpose. Okay. So with this, this is spectral theorem. But I have not completed, so I'll go back one slide, the statement. Yeah. The theorem, what it says, look at the second one, matrix version. So from the example, you can understand if A is a real matrix, symmetric matrix, then always I can do this. A, Q, this is diagonal, Q transpose. Why I put Q transpose? Because if Q is here, then Q transpose is the inverse of Q. Okay. Where Q is an orthogonal matrix and lambda is a diagonal matrix. That's it. But otherwise also true. If you have any real matrix with this, if you are able to diagonalize orthogonally, diagonalize using orthogonal matrix like this, then this matrix has to be square. Sorry, symmetric. This matrix has to be symmetric. Okay. So what is the observation you have to make it now? The eigenvalue, eigenvector, what you are finding? Any one of you? By definition, what it means? Sir, can you go back to one slide? That D, sir. D. Yeah. See here, I'm saying that any vector, suppose if I take 1 comma 0 and multiply with this matrix, 1 comma 0 I am putting here and multiply this matrix with 1 comma 0, the output will be 3 comma 0. That I can write it as 3 into 1 comma 0. So Ax equal to lambda x. The input is 1 comma 0. When I operating with this matrix, the output is 3 comma 0. That I can write it as 3 times of 1 comma 0. So it's like if you take x as 1 comma 0, Ax equal to some lambda. Lambda is 3 and x is 1 comma 0. So this is that eigenvalue problem. That is that matrix equation. Ax equal to lambda x. So x is the eigenvector correspond to the lambda. The x should be non-zero. That's what you are finding. So as application, what you are doing, so at the nutshell, now you can think about matrix will rotate the matrix, it moves the vector here and there. That's what we know. But we are looking for a special vector for a given matrix. When I'm operating with this matrix, it has to stay in the same direction. It should not it should not rotate or something. I'm looking for a given matrix. We are looking for a non-zero vector x. when I'm operating on that, that is AX, that should be in the same direction as X. So it has to be some multiple of X. It can stretch, but it should not rotate too much. Okay. So such a vector, we are giving that name called eigenvector. But to find eigenvector, we have to find the eigenvalue. So eigenvalue tell that how much it's stretched in the direction, how much the input stretched by this matrix. So the direction, stretching, rotation, scaling, etc. These are the whole idea about. So in a matrix with full numbers, the matrix will do rotation as well as stretching with some reflection also. Okay, that also comes into picture. So all the matrix will do this much only. So the modern theory, what it asking us, okay, can you split this? For example, rotation and the stretching happen, no? Or translation happening. Okay. If I give a matrix, can you find the part of that matrix which do the rotation and which do the scaling? Can you split it? That means they're asking that. That is a modern. That has a nice application in what do you call
Huh?
the singular decomposition. That will reduce the data much
ಕೇಳಿಸ್ತಾ ಇಲ್ಲ.
actually. Okay. This is all about spectral theorem. Again, I'm telling, I didn't write any equation. I didn't write any theory. Just a feel about. You have to read that statement again to get into this idea. Okay. It is full understanding about diagram understanding. That's it. This is up to that spectral theorems. At this stage, anyone have questions? Any queries or any doubts? Excuse me for not able to connect it because I thought of writing more in my screen actually, but due to I am not able to share it. For that, excuse me. That sorry. Otherwise, whatever I discussed now, I might have wrote and I have shown to you. Okay. Please excuse for that. Any ideas? Okay. Now
Sir,
the next question.
right now you
Yeah.
proceed, sir. We will ask at the last.
Okay. How much time left,
We
sir?
are left out with another 20 minutes, sir.
20 minutes. Okay. I'll take some 2 minutes break, sir. 2 minutes, sir.
Okay, okay, sir.
2 minutes gap. Only 2 minutes.
Participants, be online. ನೋಡ್ತೀನಿ ಇರಪ್ಪ ನೋಡ್ತೀನಿ ಏನ್ರಿ ಹೆಸರು ಇದು? ಜನಿಗಲ ಅಂಜೇಯ. ಹಾ, ಜನಿಗಲ ಅಂತ ಇದೆ ನೋಡಿ ಒಂದು. ಜನಿಗಲ ಅಂಜೇಯ ಅಂತ.
Okay, sir. Shall I continue?
Yeah, yes,
Hello.
sir. You can proceed.
Okay. And before going to the next slide, just think about so far that concept what I have discussed. It's all for the square matrix because that it's a square matrix, and we are looking for eigenvalue eigenvector. And for symmetric matrix, that can be decomposed into, that means that can be diagonalized specially. The symmetric matrix can be diagonalized specially with orthogonal matrix. That's what spectral theorem. But in from the application, if you look at the matrix, suppose if you take some image from the, especially from the image processing, if you take some image, what it will do? It has some pixels. It will take it as pixels and it gives a matrix. Even a small image will give a big matrix. Okay, it's a big matrix. It will give, and you can see that that it need not be a square matrix because I'm going to talk about something called singular value decomposition. That is the eigenvector of some other matrix. Okay, to understand that we are extending the idea of this to the
Chat box,
general
sir.
matrix. That means the matrix need not be a
Again,
square
I need to
matrix.
go to the
So
meeting
if
of
it is
yours.
not a square
In
matrix,
between, I
we
cannot
can't,
go.
by definition, we can't find that, what do you call that, eigenvalue eigenvector. We get a self mapping. It should be self mapping.
So one
So
second.
now for general m by n
Uh,
matrix, what can we do?
actually, I'm sharing, sir. Now
Okay.
I'm sharing
Uh,
myself.
but
I'm sharing
the
the
beauty
slides.
is this:
That's why.
you start with some matrix,
Okay, sir.
you
Okay,
start
sir.
with some matrix, and you take any m by n matrix, look at the transpose. The transpose is going to be n by m matrix. N by m. If A is a m by n matrix where m not equal to n, and A transpose is going to be n by m matrix. A transpose, I hope everyone knows it's a transpose of that. So n by m. So now I'm finding two things from this two matrix. A transpose, uh, the size of A into A transpose will be what? M by M matrix. It is a square matrix. Similarly, A transpose A is also a square matrix, but the dimension is different. N by N, N by N matrix. So you start with the matrix M by N. Its transpose is N by M. Take the product in two way. A transpose, A transpose A. So one will be M by M matrix, another one will be M by M. Now, not only this size will be square. The beauty is A transpose is always symmetric. You can verify. For given any matrix A transpose if you take the product of that matrix with its transpose, that is always symmetric. Okay. Similarly, A transpose A is also symmetric. So we got the symmetric matrix for a given A. Okay. These are all some entries playing inside with A only. We are getting more information actually. A transpose, A transpose A. And I can apply the spectral theorem there actually. This A transpose you can decompose into diagonal matrix with the help of orthogonal matrix. Similarly, A transpose A also. So now these and the eigenvector correspond to that A transpose and A transpose A. You put it in two different matrix along with a diagonal which we call it as a singular value. The square root of the eigenvalue of, at this point I hope you understand this. A need not be square. A transpose, A transpose is square. A transpose is A is also square. And both these matrices are symmetric. So I can apply the spectral theorem. That means what is the beauty of the spectral theorem is for the symmetric matrix the eigenvalue will be real. Okay. So that you can use that. As I said, I'm not touching the theory too much, just giving the idea. and you can get orthogonal vectors also there. So for A transpose, find the eigenvalue and the corresponding eigenvectors. Using that eigenvectors, form one matrix. Call it as U. Other matrix A transpose means that. Okay, A transpose A. You find the same stuff, eigenvalue and eigenvector for that matrix, and you can keep that eigenvector with the eigenvector form one matrix that you call as a V. Okay. What is the beauty here? Is this a theory? The eigenvalues, what will be the relation between the eigenvalue of A transpose and A transpose A? The one important thing what we can show, the eigenvalues, the non-zero eigenvalues of these matrices, A transpose and A transpose will be same. That means all the non-zero eigenvalues will be equal. Rest of them will be zero. This is the important picture and observation about this matrix. So now, if it is a symmetric matrix, we can decompose using spectral theorem. But if it is not the square matrix, we find with the help of these two matrices, we can find U as a one matrix and V as a one matrix. And you can write A as U diagonal V transpose. This is called singular decomposition. Okay. U diagonal V transpose. What do you mean by that? U is the eigenvector of A transpose and V is the eigenvector of A
A
transpose
transpose.
A. Okay. You have to put it properly that which one is that. Okay. This decomposition is called singular decomposition. And what are the singular values? The singular values are nothing but the square root of the eigenvalues of A transpose or A transpose A. That's it. Because both will be same. Okay. And this singular decomposition playing a vital role in dimensional reduction and compression. Okay. Compression means you know that if you have an image, many times you might have applied for many things. In that, in the online, they want to reduce the space. They will give, you have to upload this material by with this size. Only 10 KB, 5 KB, 4 KB photos will be like this, and some other document mean they'll keep it for some 25 KB or sometimes MP. Okay, it depends. Then what will you do in online application? We used to compress it, right? So what it does actually, for that image, there will be some matrix behind that. With that, they have the algorithm with SVD, and they will give that output with minimum quality. With the minimum quality means it will be little dull compared to the thickness, brightness of that original one. But still, the information we won't lose it. Okay. We don't want too much of information. With the maximum information, we can retrace this guy. That's what the whole thing about the singular decomposition, the crux. But how it's happening, it's with the help of some other idea that I need. Sorry for again that I am not able to share it. So now please keep this in mind. Okay. So one idea is you can extend that idea, spectral idea to that in this way, not the direct extension. For a given matrix, you can find A transpose A transpose, and do this. Okay, then you'll get a singular decomposition. You'll get a three parts. You have to understand U is the eigenvectors of some A transpose, and V is the eigenvector of the matrix formed with the eigenvectors of A transpose A. Okay. Now, this SVD, that is SVD. Okay, I would like to talk about more thing, but due to that slide, I'm not talking. Now, okay, this you keep it in some other side. Now let's do this for, this is what I'm going to talk is something called principal compound analysis. Means, now only I told in the last diagram that 2, 1, 1, 2 matrix is having some tight package with X and Y. X and Y are related tightly. but we can't change the direction. In that direction, we can break it into
sir.
simple.
Sir.
That's what you have seen. Okay, this what is in the slide you are telling that. Okay, if you go with this direction,
ರವಿಕುಮಾರ್
given object you
ಚಾಟ್ ಬಾಕ್ಸ್
rotate
ಇವಾಗ
with this
ಎನೇಬಲ್ ಇದೆಯಾ ನೋಡಿ.
matrix, the rightmost matrix, it will do the rotation. In that direction, it will be very proper stretching alone will happen and come back to the original. So by understanding the problem, you can come back. That's what the whole matrix will do. Okay. Now,
ಇಲ್ವಾ?
in this matrix, if you have data, okay, in principal common analysis, what do you mean by that? If you take some statistical data, it is going to be our some application data. Okay, for this. Okay, now clean up everything in your mind. What I said about singular decomposition. Try to imagine this question. Okay, assume there is a uh, something is some action is happening in one place actually. Okay, something it some oscillation of a spring is happening or something like ball is oscillating. You are having hanging something in that roof of your room with some balls attached with the spring, and it has some motions, and
ಡೆಸ್ಕ್ಟಾಪ್
it
ಅಲ್ಲಿ
is
ನೋಡಿ.
moving in the motion like this vertical only.
ಹಾ,
The weight
ಮೊಬೈಲ್
is
ಅಲ್ಲಿ ಬೇಡ, ಡೆಸ್ಕ್ಟಾಪ್
pulling
ಅಲ್ಲಿ
with
ನೋಡಿ.
the gravity, and the spring is forcing, pulling it back with the spring constant. So the oscillation is up and down happening. Now assume that
ಹಾ,
there are some lot of equation physically you know how to solve it. But now I want to tell
ಆಗ್ತಾ
something
ಇಲ್ವಾ?
about data driven things. Data driven means with if I capture this action with some sort of data, if I have some sort of data with that, then I can retrace this action. But to capture this action, if I give many
No, sir. It's
instrument
not
to capture this, the question is,
able to chat over there, sir.
do I need all this information? Do I need the information from all these
ಹಾ,
some material what I got? Suppose if you assume that
I
the
see, I see.
action is happening
Okay.
with the spring,
It's okay, sir.
and you are keeping around that some 5 cameras in different
Q
angles,
ಏನು?
assume, okay, and you are
Questions.
capturing it. One moment, I want to study about this
Data
oscillation.
Q
You are
on
giving
E.
the 5 cameras.
ಹಾ, ಹಾ, ಹಾ,
The action is happening on
ಹಾ,
the
ಹಾ.
three-dimensional space, but whatever that photo will take is a
Okay,
two-dimensional
sir.
object. So at each moment, it will create some
Okay,
image
okay, okay, sir.
which has some
Okay, okay,
two-dimensional
okay. I
picture.
will
It has
post
a
that, sir.
pixel.
I will post
Okay.
that.
So to understand this, to get a picture about this, we have a x coordinate and y coordinate in this camera 1, camera 2, camera 3, camera 4. So all this information, if you gather, club it together, you will get that whole picture. That's what. But my question is now, the data I'm having, the xy coordinates of at each position. Okay. Can I retrace that guy with without losing the information? That's what. And not only that, do I need all these 5 cameras information, or is there any relation dependency between the data of these cameras? Okay, we don't know. We don't know that actually. So that can be reduced with the help of this singular this what do you call that? Dimensional you can reduce, the redundancy you can reduce PCA. Okay, and we'll to do that, what they will see, they will compare each and every information of XY with all other XYs. XY with
ಓಪನ್ ಆಗ್ತಾ
all
ಇಲ್ಲ
other
ಇದು.
XYs,
ನಿಮ್ದ್ರಲ್ಲಿ ಕ್ಯೂ ಎ ಅಂತ ಬರ್ತಿದೆ.
and find that statistical constant like variance of X with X. If X and Y are coming, different things coming, then
ಕ್ಯೂ
covariance
ಎ
they
ಅಂತ
will find.
ಬರ್ತಾ ಇದೆ ನೋಡಿ ಕ್ವಶನ್ಸ್.
And this constants, variance and covariance, they with that they will form a
ನನ್ನ ಕ್ಯಾಮ್ರಾ ಆನ್
matrix.
ಆಗುತ್ತೆ, ನಿಮ್ದಾಗಲ್ಲ.
That matrix will be symmetric, and that will
ಮೇ ಬಿ ನಾನು
satisfy
ಆರ್ಗನೈಸ್
something
ಮಾಡ್ತಾ
called
ಇಲ್ವೋ ಅದಕ್ಕೋ
Markov
ಏನೋ
matrix.
ಗೊತ್ತಿಲ್ಲ.
Okay, and
ನೋಡಿ
for
ಇವಾಗ
that
ಕ್ಯಾಮ್ರಾಗಳು
matrix they
ಓಡೋಗ್ಬಿಟ್ರೆ
will
ಆನ್
do
ಆಗ್ಬಿಡುತ್ತೆ
that
ತೋರ್ಸ್ಲಾ?
apply that this eigenvalue
ಇಲ್ಲಿ
decomposition,
ಎಲ್ಲೂ
singular
ಕ್ಯೂ ಎ
decomposition.
ಬರ್ತಾನೆ ಇಲ್ಲ ನಿಮ್ಗೆ,
Then
ಅದಕ್ಕೆ
what you
ನಿಮ್ದ್ರಲ್ಲಿ ಕ್ಯೂ ಎ
call
ಬರುತ್ತೆ.
that
ನನಗೆ
will
ನನಗೆ ಚಾಟ್ ಬಾಕ್ಸ್ ಓಪನ್
project
ಆಗುತ್ತೆ ನೋಡಿ, ಇಲ್ಲಿ
the
ಆಗ್ತಾ ಇದೆ
all the
ನಿಮ್ಗೆ.
higher
ಶೋ
dimensional
ಚಾಟ್
vector to
ಬಬಲ್ಸ್.
the lower dimensional plane
ಹಾ,
like this,
ಕ್ಯೂ ಎ
where
ನೋಡಿದ್ರೆ
that
ಚಾಟ್
data
ಬಬಲ್ಸ್
are spread
ಅಲ್ಲಿ
too much.
ಅದು ಸ್ಕ್ರೀನ್ ಶಾಟ್ ಹೊಡೆದ್ಬಿಟ್ಟು
From
ಅಲ್ಲಿ
that
ಹಾಕಿ
they will do
ಇವಾಗ.
some study. Okay, that's
back
the
हो
whole
गया.
point about this
If you
SVD.
have any doubts,
And sir, can you move that back? That previous, the starting slide.
queries ಹಾಕಿ
No,
ಅಂತ ಹಾಕಿ.
back. This is the original data assume. Okay. So no, forward. Yeah. Now you take this student's data. This data you can take it in different way, but I kept it as like classical things like marks. But there are a lot of applications which will talk about the biostatistics and everything. It's talk about gene 1, gene 2, gene 3, and the patient name, diseases, and the test. Many data will be there. But here I have taken two data. For 10 students, I have taken the max marks and physics marks. And this I have plotted here. Just I have to give the impression of what it's doing in that principal common analysis. Okay. So this is statistics, a statistical idea. Now this data is spread here and there. Okay. Now they will try to see that variance, how much it is variant. Okay. Variance, using the variance they will do. Okay. Next slide, sir. Now you know how to find the mean of that each data. That x bar will be given the average arithmetic mean. Similarly, y bar you can find this. So the mean is something in the center. That is the center of the object, mass, center of the data, mass of center of mass. Okay. Now mathematically, what you have done, we are going to see again. The ship problem, what you have done, we have origin, we have changed from this center to this. I am going to change now. The same idea. Next, sir. Yeah, what I am doing is shifting, that is changing the origin. Changing the origin means I am going to uh, subtract this mean from each data for x and y, and the new data I am going to represent with xc and yc, and the mean of that is going to be 0. Next slide, sir. Next. Yeah, this only. See, the original data previous. Yeah, the original data is x and y, and you know x is some 56 something, so you can see that if you subtract that each x bar from each x, you will get this column, the data, new data. Yc is this. Really what you are doing, this is one of the important idea in machine learning. When you are given a data, you have to make it in nice way. You have to move that origin to the center of the data. Okay, by taking the average, that point it is moved. By subtracting this we can do. Okay, so now the data are well arranged. That's what they call in machine learning. Okay, but center the data about the mean. And next slide, sir. And immediately they'll find what is the variance from that mean. Yeah, this is a covariance matrix. Covariance matrix means the first thing what they are finding is the variance of x. Variance of x alone. Okay. The second, see, there are 4 entries. The first position A11 is A11 is variance of x. A22 is variance of y. And this A first row second column is the covariance of that. Covariance is what? You are finding that you have to take the x bar, find the difference of each point from this x bar, square it, and find the average of this data. So this is that measures of dispersion in statistics. What you'll read it, how much the center will give about something, the point in center. It will not give the clear idea. And they will try to study how much the data are spread. Okay. That will be given by measures of dispersions, and especially the standard deviation. The square of the standard deviation is variance. And if you have two data to compare, then I can find the variance of x and y. Similarly, it is going to be variance of y and x. Okay. Then this covariance, if you know the formula, if you find this and substitute here, now come back to our matrix idea. This is a symmetric matrix. Now you can do the eigen decomposition. Find it, sir. Next, find the eigenvalue and eigenvector for this matrix. Sir, next slide. Yeah, this is the eigenvalue for this, and this is the eigenvalue for that. Two eigenvalues and the corresponding eigenvectors are there. Now this gives the principal direction. Okay, in this direction, you can rotate. Hey, sorry, you can move to the next slide, sir. Yeah, the red line is with the V1 vector. The direction of the original axis is black one, and data are spread like this. This is a centered with mass. Centered. The data are centered with mean actually. And now this red line, how we form not arbitrary line. We found that eigenvectors of that covariance matrix for a given data, and this data I have taken. Now, see, this line will capture the maximum, how that distributed. Okay, the maximum distribution is captured. So this is along the direction of the first one. Similarly, blue line is the second vector, eigenvector. So now what we'll try to look at that, what is the idea behind that? The data are high dimensional data, but they will try to project onto the two-dimensional or three-dimensional, and people used to study the observe about that problem. Okay, why two-dimensional, three-dimensional? Because we are limited to the two-dimensional. For us, it is easy to understand. Okay, so the mechanism is possible via SPD. So now next slide, sir. The two directions are from the two eigenvectors. Now, if you project that original vector onto the first one, you see the maximum data captured. Okay, the variation, the direction which that the data are maximally distributed in this direction. Okay, so this itself is enough to understand the data now. No need to bother, because that along the blue line there is a variation is very less. That also you can see. So next slide.
ಹೇಳ್ಬೇಕೇನಪ್ಪ ಬನ್ನಿ ಇಲ್ಲಿ.
So next slide. Next. Next. Next, sir. That's all. See here. Similarly, I can project.
ಇರುತ್ತೆ.
Yeah. Similarly, sir, next one. Similarly, you can project the origin data to this PC2 axis also. Okay. So like this, they will try to study that this variance is, you see that two line. Last slide you can see.
ಓಪನ್ ಇದು ಲೇಡೀಸ್ ವಾಶ್ರೂಮ್ ಓಪನ್ ಮಾಡಿ.
That last slide. One more will be there, it seems. No. Next, sir. Next. Next.
ಮೂನೇ ಆಯ್ತಲ್ವಲ್ರಿ ಸ್ಲೈಡ್ಸ್.
I kept both actually. Next, sir.
ಕುಮಾರ್ ಸ್ಲೈಡ್ ಮೂವ್ ಆಗ್ತಾ ಇಲ್ಲ.
Okay. So this is the picture. Okay. So the variance along this PC1 is more. So that direction will give you the more information about the data.
ವಿದ್ಯಾಶ್ರೀಗೆ ಹೇಳ್ಬಿಡಿ ಅದು ಇದಕ್ಕೆ
Okay.
ಹೋಗಕ್ಕೆ.
And you can study about the problem. That's what that. So PC1, the PC2 is this, captures the secondary variance orthogram.
ಮುಗಿಲಿ.
So there are two kind of problem. To understand that dimensional directionally, they'll go for that maximum this PC1 to get the information. Okay, and to reduce the noise, they will go for the lower one, PC2 here. They will remove that actually by reducing the noise. These are the noise. Okay, and these data are enough to capture the whole things. Capture means to understand the whole thing. That's it. With this, I'm stopping because without writing, I can't move further. Is that okay, sir? Shall I stop?
Yeah, okay, sir.
Again, for the audience, excuse me for that technical issues. Okay. Uh, I know that will be little hard, but still, any queries you can ask, doubts are, I'm interested in answering. And I can learn from your doubts also.
Yeah, now anyone having doubts, you can raise your hands, or else you can put in Q&A, question and answer. There you can post. Yeah, Darshan Dharma Singh. Yeah, Dharma Singh. Yeah, you can unmute yourself and speak out with Dharma Singh. Yeah, you can ask your question. Unmute yourself and ask. Dr. Dharma Dharm Singh. Dr. Dharm Singh. Yeah, Dr. Dharm Singh. Yeah, I have made you to unmute yourself and you can ask your queries. Hey, ಇದೇನಾಗೋಯ್ತು ಟೀಮೇ ಹೊಟ್ಟೋಯ್ತು. ಕ್ಲೋಸ್ ಆಗೋಯ್ತು. ಕ್ಲೋಸ್ ಆಗೋಯ್ತು. ಹ್ಞೂ ಇಲ್ಲ, ನನ್ ಕ್ಲೋಸ್ ಆಗೋಯ್ತು.